Good morning. Thank you very much for the opportunity to present in this conference, and we will now present our work on predicting the Portuguese GDP using three different computational techniques, which are principal component analysis, confirmatory factor analysis, and random forest. Starting by the introduction, we have to say that gross domestic product, which is the GDP, is a measure of the created value through the production of goods and services in a country during a certain period, and it is the most important indicator to capture a country's economic activity. Although it is not directly related to the well-being of a population, it is relevant for a country's development as it is numerically seen in the Human Development Index. Furthermore, some authors explore correlations between the chosen variables and GDP, some explore causality relations, and others predict GDP. And in this work, we intend to see if it's possible to predict the Portuguese GDP using a set of variables that we will present next. About the structure of the work, it's structured as follows. So now we have been introducing the general topic and motivating the topic. And in the next section, we will perform a literature review. In the third section, we will present the empirical work. Section 4 comprises the presentation and the discussion of the results, and the conclusions are presented in section 5.
In this section, our intention was to overview some of the literature on this topic by presenting recent scientific articles that back our choice of variables. GDP is widely studied in the literature across time as it is a classical and fundamental research topic. While some authors try to predict it, others find explanatory variables to its growth and depreciation by using standard data analysis techniques. In these studies, multiple techniques such as the non-parametric frontier method and the application of econometric models such as ARCH and GARCH are used to find a correlation between GDP and other indicators. Some studies also allowed us to show the predictive power of GDP using forecasting tools such as the OLS approach.
As for the empirical work, based on the previous section, we built the following table, which presents the variables that will initially be considered in our study and the literature that also uses each one of them alongside with the years for which there is data available in our sources, which are also presented. Then we prepared our data according to the study that we are trying to do. So of course we lagged the variables and removed the appropriate lines accordingly. And then we performed the correlation analysis by building the following correlation matrix. We then built a new data set by eliminating some of the highly correlated variables for which we considered high correlation values greater or equal than 0.85 in absolute value. This allowed us to extend the time frame of the observations, and we then replaced the Psi20 index by the DAX30, and that allowed us to extend our period of observations from 1988 to 2020.
In this subsection, we will talk about the three data analysis techniques that we used, and we will start with the PCA test. PCA converts a set of observations that can be correlated into a set of values of linearly uncorrelated variables. Each component is chosen in a way that minimizes the loss of information, so that they would still describe most of the variance. Before applying the PCA, we look at the variables with higher correlation. To do that, we created a list that contained all the variables with correlation higher or equal to 0.85 and selected those that should be removed. After this analysis, it is viable to apply the PCA test. First, the dataset was separated into training and test set, with the training set representing 80% of the set and the test set the other 20%. After that, the data was standardized. Since we wanted to minimize the loss of information as much as possible, we reduced our dataset to 5 dimensions, since with these dimensions we had around 95% of the variance explained. Then, we tested the model using an OLES regression and, as it is shown, the accuracy of both the training and test set are very good, and the model is not overfitting.
This case study seems to be perfect for the application of confirmatory factor analysis, but there are huge differences in the scales of our dataset, so we standardized the variables, but we noticed that many are still highly correlated. To apply the confirmatory factor analysis, we must check the factor validity of the model, and so we compute the Kaisermeyer-Olkin sample suitability index and the Bartlett's t-test for sphericity. We retrieve a KMO value of 0.81 and the Bartlett's t-test for sphericity's p-value is less than 0.001, which allows us to conclude that the sample is well suitable for the application of the confirmatory factor analysis. To check the adequate number of factors, we see the eigenvalues and observe that 3 of them are greater than 1, and so we proceed with the choice of 3 factors. We build the factors using the usual criterion after applying the confirmatory factor analysis followed by a varimax rotation, and then we choose for each factor the loadings which are greater than 0.5. We then build the factors and check their internal consistency using Cronbach's alpha. Their values are presented and they are considered as acceptable. We then checked the factors and computed their variance inflation factors, and they were all very close to 1, which indicates no multicollinearity. And then we test the model using a regression, separating the sample into training and test subsets using a 80-20 split, and the accuracy was very high in both the training and the test subsets, which indicates that the model is not overfitting.
The last technique used was the random forest. Random forests seek to affect correlation reduction by a further injection of randomness. It constructs a lot of decision trees in training time. For regression tasks, the mean or average prediction of the individual trees is returned. The dataset used in this part is the same one that was used in the PCA test. As such, the training and test sets were already defined. We used the function random forest regressor with 1000 estimators, which represents the number of trees, and the maximum depth of the tree of tree. The accuracy on the training set was 0.987, while on the test set was 0.932. This means that, as in the PCA test, the accuracy on both the training and the test set was high, and no evidence of overfit was found.
So, having our models presented in the previous section, our goal now is to compare them and identify their advantages and shortcomings. Here we can see the parameters of PCA and CFA models. In both of them, the values of the R-squared and the R-squared from the sample are greater than 0.95, indicating a great fit without reasons to think about the model is overfitting the data as seen previously. The kurtosis values are close to 3 and the skewnnesses are close to 0, which indicates that the residuals are normally distributed. The condition numbers of both models are low, indicating no multicollinearity, and the Derby-Watson test verifies the homoscedasticity, which given our sample size, it is within the limits according to the literature. Besides that, R squared is less than the Durbin-Watson statistic in both cases, and this indicates the models are not forced. In this table we present a summary of the results, but now using common error measures. The values presented in this table are low because of the scale in which we are measuring GDP. These values of R squared in a work in the field of economics are extremely high and worth noticing, which is surprising given the context of our study. The best model was a linear regression obtained using CFA, then the linear regression preceded by the principal component analysis, and then the random forest method. To visualize the fit of the models, the GDP prediction were merged and plotted, and we can see here the PCA prediction with the observed GDP, then the factor analysis method, and the random forest. And they all look good predictions for the observed data. About the conclusion, we'll do now a brief review of what we have done in this work. We try to predict the GDP using three different computational techniques. To achieve it, we started by carrying out a literature review on the topic, motivating our choice of variables, and presenting at least a reference supporting each one of the variables we chose. Then we showed how a simple ordinary least square regression is unable to provide a good fit for our model, which motivates the necessity for more advanced analysis techniques. The first technique we applied was the principal component analysis, and the results were very satisfactory. We highlight that there was no sign of overfitting, the R squared was really high, and we avoided the strong issue of multiple linearity. Then we studied the conditions of the application of factor analysis to our dataset, and several application attempts were made.
We conclude that there is a trade-off between the easiness to apply each one of the aforementioned statistical techniques and the quality of the models. The results of our study allow us to say that the objectives were fulfilled and that a solid prediction of the Portuguese GDP were achieved. This study can also help policymakers to better understand the impact of their policies on the GDP.